Hi, I'm Gojisin and I will do the demonstration of Project 3 in this video. So the design I choose is GCD calculator. It will calculate the greatest common divisor for two input. So this one is the top module of the GCD calculator, and this one is the DU of the GCD calculator, and this one is the CU of the GCD calculator. Next, this one is the test bench of the GCD calculator to test and verify the design. In this test bench, I have insert 21 input to verify my design. So next, I will directly simulate using Synopsys BCS to verify my design. So this is the command to be used to trigger the Synopsys BCS. So next, I will use /simv to get the newest and make sure the result is up to date. Next, I will run dbe and to view the waveform. So at here, I will open database, click on GCD calculator test bench UPD, select all the waveform, and add to wave. So at here, as you can see, when reset equal to 1, there will no input be accepted because I am using the post edge reset. So when reset equal to 1, all the output will become 0. And then I'm also using post edge enable. When enable equal to 1, the GCD calculator will function. So when enable equal to 0, all the answer equal to 0. So when reset equal to 0 and when enable equal to 1, the GCD calculator will start its functionality. So at here, it can be seen that when input P equal to 4 and input Q equal to 8, the done signal is accepted and the output is 4. So the greatest common divisor for 4 and 8 is 4. The output will be accepted after the done signal accepted. Next, this one is the second example. The input P is equal to 2 and the input Q is equal to 8. So the greatest common divisor is 2. And the third example, when input Q equal to 5 and input Q equal to 10, the output of the greatest common divisor is 5. So that's all for the verification of the waveform. Next, we will proceed to the DC shell to get the PPA analysis. So I will writing two scripts to run the DC shell. The first one is DC constraint and the second one is the DC run.tcl. So inside the DC constraint.tcl, we will set the maximum area is 0 and clock period 5, uncertainty 0.05, clock latency 1, clock transition 0.5, input delay 1, output delay 1, lot 0.001 picofarad, input transition 0.8, and driving cell I am using MBUFF X4 LVT inside the size 32 nanometer design. And the operating condition is SS0P95V125C as mentioned inside the project and according to the project constraint given. So this one is the DC run.tcl file. We'll read the Verilog file first and then set the current design and link and get the source from DC constraint. Later we'll write the DDC file, site file, and SDC file. And we'll also get the report for the setup timing, hold time, power time, and clock and power, area, POR, timing, and clock. So next I will run the DC shell command. So this one is the DC shell command to let us get the PPA analysis report. So next I will go to the report file to view the timing, area, and power file. This one is the area file. This one is the clock file. This one is the setup time file. This one is the hold time file. And this one is the power file. So next I will go to the ICC2 compiler to do the flow planning. This one is the ICC constraint file to be used to create the flow planning. So next I will use the dashboard also to run the ICC shell. So this one is the command I use. So as you can see, this one is the layout of our GCD calculator. I will manually delete for the VDD here to avoid overlap. So this one is our final layout for the GCD calculator. And I'll save it. So next I will go to the ICC output text file to see the DVS and the LVS result. So this is the DRC report for the GCD calculator. So as you can see here, the DRC summary, the total violation is 0. And next I will go to the LVS report. So this one is the LVS report. And LVS is N and no error file. Next I will go to the netlist file. So this is all the file generated by ICC shell. And I will go to the report file. This is the ICC error file. And this one is the ICC timing file. So as you can see, the slack is positive, so no violation occur. And this one is the ICC power file. The whole time is also positive, so no violation. Lastly, I will go to Synopsys PT to do the SDA. So as you can see, this one is the PT constraint.tcl file. The constraint is the same as the constraint inside the dc.tcl file. So next, I will run this command to go inside the PT shell and get the PPA analysis report. Next, I will go to the report file to view the report. So this is all the report file generated by PT shell. So I will go to the timing file. So this one is the whole time. So as you can see, the slack is also positive. And this one is the setup file, setup timing file. The slack is also positive, so no violation occur. This one is the annotated parasitic file. This one is the power file. And we can view the area used inside the QOR file. I will go inside run log also to see whether all the thing is correctly being inserted. So since all the thing is 1, so all the thing is able to be accepted successfully. So that's all for the baseline design. And next we will proceed to the optimized design. The objective of this project is to optimize the power, performance, and area PPA. So next, I will do the optimized design in this video also. So the same procedure will be performed. First, I will go to the verification, and the GCT calculator code is the same as the baseline. The test bench code is also same as the baseline. So firstly, I will verify my design also using the Synosys VCS. The command apply is also same as the baseline. So I will also use /simv to make sure the result is up to date. So next, I will use DVD and to see the waveform also. So this one is the output waveform obtained from the GCT calculator. The waveform will be the same as the baseline. So as you can see here, when the input is 4 and 8, the common is 4. And when the input is 2 and 8, the common is 2. And when the input is 5 and 10, the common is 5. So this next I will proceed to the DC shell simulation. So this one is the DC shell constraint file. All the setting is the same as the baseline. This one is the DC run.tcl file. The only difference is I'm using get clock at here to ensure the clock gating is used in this optimized design. So next, I will simulate using DC shell to get the PPA report. So the command used is also same as the before. So we will go to the report to view the PPA report. So this one is the area report. This one is the clock report. This one is the hold time report. The slack is positive, so no violation. This one is the setup time report. The slack is also positive, so no violation. And lastly, this one is the power report. Next, we will go inside the ICC shell to generate the flow planning. So this one is the ICC.constraint TCL file. It is also same as the baseline ICC constraint file. So next, I will run the ICC shell in dashboard to get the PPA report. So this one is the layout of the GCT calculator optimized design. I will also manually delete the VDD and PWSS to avoid the overlap. Save and exit. Next, I will go to the output file to see the DRC and LES report. So as we can see here, this is the LES report. And we can see here, this is the DRC report. So the total variation is 0. Next, I will go to the report file to see the ICC area. So this is the ICC area. This is the ICC constraint file. This is the ICC power file. This one is the hold time file. So slack is positive, no violation. This is the setup time file. Slack is also positive, so no violation. Next, I will go to PT shell to get the PPA analysis report. So this one is the constraint file of PT shell. It is also the same as the baseline design. So I will run the PT shell in batch mode also using the same command with the baseline. So next, I will click on view report to see the report. So this one is the annotated parasitic report. This one is the constraint report. This one is the power report. This one is the hold time report. So slack is positive, no violation. This one is the setup time report. Slack is also positive, so no violation. From the report QOR, we can see the area in this design. So next, I will show to you for the comparison between baseline and the optimized and see whether the get clock is. So next, I will show you the comparison between the optimized and the baseline design to see whether clock gating is useful in optimize the performance, power, and area. So at the left side is the clock gating power up, and the right side is the without clock gating. So as we can see, the total power has been reduced when using the clock gating function. And next is the area. So as we can see, this one is without clock gating. The total cell area is 423. And with clock gating, the total cell area is 401. So clock gating is also able to reduce the cell area. And lastly is the timing comparison. So without clock gating, the slack is 2.4 and the critical path delay is 1.6. And with clock gating, the critical path delay is 1.56 and the slack is 2.44. Overall, the design is meet the slack and don't have any violation. And with clock gating, we can be seen that the data arrival time, which is the critical path delay, is reduced. So it can be concluded that the clock gating is able to optimize the performance, power, and area. So that's all from me for this demonstration video. Thank you.